Welcome to Thorlabs. My name is Paul, and today I will demonstrate the approach I use when collimating a highly divergent light source with a relatively large emitter size. For today's demonstration, I'll be using an LED current controller, a 505 nanometer mounted LED, two aspheric lenses, a viewing screen, and a thermal power meter and sensor. These lenses have different focal lengths and numerical apertures to illustrate the trade-offs between beam divergence and beam power when collimating this LED. There are two important LED properties to consider when collimating light. One is that LEDs emit light over a wide angular range, described by the LED's divergence or viewing angle. This angle measures the full width half max of the intensity profile with respect to the full angular range. If the goal is to collect the maximum amount of light from the LED, the lens's numerical aperture, or NA, is the most important parameter. The NA of the lens describes the largest cone of light the lens can collect. A lens with a larger NA will collect more light from a highly divergent source, but it may not be possible to find a collimating lens with an NA large enough to collect all of the light. Often, it can even be difficult to find a lens with an NA large enough to collect all of the light across the LED's full viewing angle. To estimate the amount of light collected by a particular lens, start with the intensity versus emission angle provided with the LED, and sum over the area of the beam captured by the lens based on the NA. One reason that choosing a collimating lens with the highest NA may not be the best approach is that optimizing the power collection does not take into account the collimated beam's divergence. The divergence of the collimated beam describes the rate at which the beam diameter increases with distance after passing through the lens, and depends on the physical dimensions of the LED and focal length of the collimating lens. Since LEDs have larger physical dimensions and large NA lenses generally have short focal lengths, we typically expect the lens that collects the maximum power to also provide the largest beam divergence, like a flashlight. As lenses with larger focal lengths are used to collimate the LED light, the divergence of the beam will decrease. As a result, choosing a collimating lens requires balancing the benefits and trade-offs between collecting more power from the LED and limiting the divergence of the collimated beam. Now let's see what happens when I collimate my LED with these two aspheric lenses. My first lens is a 2-inch diameter aspheric condenser lens with 0.76 NA and 32 mm focal length. I expect the high numerical aperture to provide high throughput, but the short distance between the LED and the lens leads to high divergence in the output beam. Even with a 0.76 NA, we still lose some of the optical power due to overfilling of the lens with this very divergent LED, so I'll use cage covers to block most of the stray light that we do not collect. I've placed this lens into my beam path with the flat side facing my LED to minimize the amount of spherical aberration. And I adjust the lens position until I see an image of the LED emitter on the viewing screen. I typically use an adjustable lens tube to perform this alignment, but today I'm using a cage system to better show the individual components and allow the system to remain unchanged when I switch lenses. Now that I see an image on the screen, I'll move my viewing screen further away from the source and adjust the lens to form another image. Iteratively pushing the image of the LED further away brings the alignment closer to producing a collimated beam, which can be thought of as forming an image an infinitely long distance away. Since space in the lab is usually limited, I like to use the divergence of the beam to set the lens position. Using this lens, we expect a divergence of about 2.5 degrees, which means the beam diameter should expand by about 27 millimeters when measured 24 inches away from the output. I'll adjust the distance between the lens and the emitter until this divergence estimate is satisfied. Now I know my output beam is collimated about as well as it can be given the focal length of my lens and the emitter size. The beam is collimated and shows no emitter structure close to the lens. Note that we can still see the emitter structure fairly well within relatively short distances. Now we'll measure the beam's power. I'll use this large plano-convex lens to focus the beam into the sensor. Having recorded the size and power of the beam allows me to calculate the irradiance. The relatively large divergence angle means the irradiance will decrease as the light travels away from the lens and the beam's area increases. I'll move the power sensor out of the way, bring the screen back into the beam path, remove the 0.76 NA lens from the system, and place the 0.24 NA 100 mm focal length aspheric lens in the cage system. I've once again placed the flat side of the lens towards the emitter. I'll optimize the collimation using the same technique as before. With this 100mm focal length lens, I expect a divergence of about 0.8 degrees. This means that over the same 24-inch distance from the output of the lens, the beam size should increase by about 8.5 millimeters. By moving the viewing screen back and forth, I can see that the collimated beam diameter remains more constant over the distance of my workspace, which also means the irradiance is more consistent. I'll measure the optical power again. We have lost a significant amount of power within our collimated beam since less of the light is captured by the lens. In this demonstration, we showed that when choosing a lens to collimate your LED, the total amount of power in the output beam depends primarily on the numerical aperture, while the divergence depends on the focal length and emitter size. As the divergence increases, the irradiance decreases over distance, resulting in less usable power within your system's clear aperture. I hope this helps you determine the compromise between beam power and divergence for your application.